Okay, so we're very happy to have Konstantin Teleman, who today he's giving two talks. The first one is today, and today he's going to tell us about Coulomb branches in 2D gauge theories.
Thank you. So it's a pleasure to be here. Whenever I thank you, Tony, for inviting me. Whenever I visit and asking myself why not here more often. So then I talk about Coulomb branches. And 2D gauge theory. And what the talk is broadly is an interpretation, let's say topological 2D, I should say, interpretation of a construction by the names now by Braverman, Winkelberg, and Nakajima. It has a background on physics work by several people, Witten, Hanani, Dimov Tigayotto, and maybe several others, so based on, let's say, based on physics ideas. And the Coulomb branch, just to very vaguely explain, the Coulomb branch is meant to be a component of the space of vacua of a gauge theory in 3 or 4 dimensions. So component of the space of vacua of 3D or 4D gauge theory. So what am I talking about in 2 dimensions? Well, I'm going to interpret in 2 dimensions and explain to what extent it controls topological gauge theories in 2 dimensions. So my interpretation that controls topological 2D gauge theory and this interpretation allows to give an easier description of it. The description is partially lucky, I think, but it's lucky in the sense that it relies on a certain space, a loop Grassmann, and having an even dimensional cell decomposition, for example. It's not that lucky, except that lots of things in topology are lucky in that same way. So there will be 2 versions of the Coulomb branch, which topology, once you get to topology, you can very easily connect them by replacing the letter H with the letter K. So if you use ordinary homology, you get what people call a 3D Coulomb branch. If you use K theory, you get what people call a 4D Coulomb branch. But the real story is that, this is going to be the last vague physics thing that I tell you, is that, so they are both 4D constructs, but they become 3-dimensional in 2 different ways. In one case, you just cross with R, and here you have something 3D, and look at translation invariant theories. So you're not seeing the 4th dimension. In the other case, you cross with a circle, have a 3D thing here, and again look at translation invariance. But actually has rotation invariance now, and now because there is topology, that gives you something interesting. If you look at topological quantities, it means you're making them equivariant to the circle action, so the ground ring is now equivariant homology of the circle, and if you localize a bit by inverting the Euler class, it becomes, so let's work over the complex number, Laurent series in a grade variable of degree 2, so suddenly your world becomes 2 periodic, you're setting 2 equals 0 to work with function, and the effect of that is convert to homological construction you're getting on this side to K-theoretic construction on that side. The homology kind of becomes K-theory, and you lose the grading collapse into a Z2 painting. So what's behind is the same intuition slash philosophy, which says that you could interpret K-theory of a space as a circle equivariant cohomology of its free loop space localized by inverting the equivariant generators. And if you are really careful, you can turn that into a precise statement, and the same is in effect here. So that explains the two different versions. Okay, so what are we studying? So we're studying gauge theory. And I'll introduce the basic object by analogy to something lower dimensional that's much better known to topologists. And then I'll make things precise and state the theorem. So, studying. Let's get this out. Gauge theory for a compact group. For a compact group G. And then assume it's connected, and maybe sometimes to make life easy, simply connected, or we can do without that. So let's say connected for now. And we're studying gauge theory in 3 dimensions. And by analogy, in 2-dimensional gauge theory, you're looking at modular bundles on a surface, and let's say for a finite group, you're counting principal bundles, and you can ask, well, if you have open surfaces with boundaries and corners, what kind of structure can you put in? And one answer is that on the boundaries, you can put representations of the group. So in 2D gauge theory for finite groups, there's an old story which has been developed, of course, but very nicely written in the paper Moore and Siegel. That's what's called an open-close TQFT from the category of representations. Of, let's say, complex representation. And these representations appear as boundary conditions from the point of view of physics. And I'll just tell you, draw one thing. It means if you take a surface, and the surface will have boundary. I'm doing something wrong here, I think. Maybe a boundary here. Like that. And you put some representations U, V, and W on each boundary component. Then you can count bundles weighted by characters of the holonomies and the boundary, weighted by holonomies, holonomy characters or traces, to get a number. You'd also get a number by counting bundles on a closed surface. So in other words, a boundary condition is what you have to put on the boundary of a surface with boundary, so it behaves like a closed surface. Physics, you get a number in that case. So, and in this case, of course, you can recover the group if you know enough about its representation category, and actually there are now loads of versions of the theorem which tell you how to reconstruct the gauge theory of the category of representations. So, I'll take the same point of view in 3 dimensions. In 3 dimensions, we'd like to say that, so in 3D, the gauge theory, if you're lucky, should be described, or maybe could be described by its boundary conditions. And the boundary conditions are meant to be higher analogs of representations, and they will be representations of geolinear categories. So higher representations in the sense the actions on differential grade of your categories. It's really going to be very interesting if you don't allow the homologic algebra. But a note of caution is needed because there are several things you could mean by that. So the theory I'll talk about has to do with topological representations. Topological representations. So again, it's learned by analogy. So representations, vector space representations, so a linear representation V gives a vector bundle over VG. Precise. There are several ways. You talk about flat vector bundles over VG. If you did that, you wouldn't have too much, but if you allow to pass the derived world, you get something more interesting. Let's say derived local systems VG. And simplest example, G acts space X, then the homology of X. G being connected, it acts trivial to the homology of X. So first you think you get nothing, but in fact if you form the bundle, the Borel construction of VG, you know the homology of that actually depends in a subtle way on the way G acts on X. That differential the spectral sequence, and they tell you that you are not really acting trivially in the homology. It's an interesting representation, just no. So that's what we're generalizing, and now we just have to say categories instead. So the first cartoon picture, which will stop at first, would be enough. So first simplifies the cartoon picture. It's a two-category of local systems or flat bundles of DG categories over VG. And again, at this level of precision, one example, one way to make it precise, you could have made it precise here in this way too. You want module categories over the full chain of VG as a commutative algebra. You just need as an equal algebra. It's commutative. And put over C, so in fact by formality I have written the homology of VG here. We try an integral theory is much more subtle, of course. And by that I mean, if you see such a category that I'm asking that there should be a T2 map. Let's put the coefficients. A T2 map to the center, the Cauchy co-chain, I should say. Co-chains of C would be its natural T2 structure. So in other words, this commutative algebra is at the center of the category. It really acts with tensor with modules and we go to category. So that's the first cartoon picture that we're looking at. Similarly, we could build a slightly simplified picture here by looking at simply modules over the homology of VG without saying modules of two algebras. That would be the simplified picture. So you could try to build a three-dimensional DQFT from this, and you find very quickly that because this string is essentially not dealing with a ring of functions on a compact algebraic variety. So the theory is not quite finite. It's a partially defined DQFT. In dimension 3, you will not be able to define all the operations you wanted. Dimensions up to below 3, you can define everything you want. So, without correcting the picture, I have a little more to correct in a second. Let me tell you what the Coulomb branch is meant to be. So the Coulomb branch.
When you said partially defined, are you talking about tiers?
Lower
tiers?
So it's defined for points, 1 manifolds and 2 manifolds. I mean, everything is defined, but on the 3-dimensional level, not everything is defined. Some operations will be defined, but in general, for example, the invariance will often be infinite. I think if you don't have dimensional, if you have Betty numbers, non-zero Betty numbers, you expect an invariance to be infinite. We'll see in a second the vector space associated with a sphere is infinite dimensional. So if you try to ask what corresponds to a sphere times a circle, that would be the dimension. That would work somewhere. So the Coulomb branch is intended to be the space, the vector space associated with associated. And it's not just a vector space as structure because you have the analog of a pair of Penn's multiplication. I'm not going to try to draw a 3D pair of Penn's. Imagine that's a two-sphere. Well, okay, there are two spheres sitting in a larger two-sphere, and the space in between is solid. So this gives rise to an E3 structure on. So it's meant to be an E3 algebra. At least if it was a completely defined theory, it would be unambiguous, but because there's some doubt about what 3-dimensional pictures are allowed, one has to think about whether it's meaningful or not. That's why it's a slightly delicate problem to understand.
Wait, Constantine, it's really a vector space you're associating?
It's a sphere, so the surface for a 3-dimensional theory is like a vector space. I mean, you're worried that it could be a DG vector space.
Well, I would think it should be if you want to consider an E3 structure.
It will be graded actually, so it'll be fine. So it'll be formal in that sense. But you're right. A priori, it's a complex of vector spaces. And if you work rationally, I think enough that will be they'll be fine with that. In K theory, actually, I have to start being a teeny bit careful with this such a bit. Okay, so the analogy again back. So as long as we do topology, the analogy is the string topology of a manifold, a compact manifold X. And the theory going with that has been known for a long time, will be generated in 2 ways. So 2 ways of producing the theory. So what we're looking for in this case is not a 2 category, which will generate a 3D theory, but just a category, and in fact it comes from an algebra in this case. So we're looking for an algebra to generate a 2D theory. Now one algebra we have available is the cochains on X, so let me use. So that's one option. And another option, which is Coulomb dual or bar dual to that, is chains on the base loop space with convolution. And, well, for example, if X is the product of all spheres, that's an easy example. And that's an exterior algebra. The other one is a symmetric algebra, where generators are in duality. And we know there's a close relation between modulus over one and modulus over the other. It's called Coulomb duality. And I guess if you insist on gradings being preserved, then it doesn't seem to matter too much which one you play with. Let's say if you're to take K theory here, the collapse grading of 2, then very quickly you see that this guy is better in many ways. There are a lot more modules over it, and also actually, regardless of grading, the augmentation module just just Q, is a finite modular over the second of a symmetric algebra, but not over the exterior algebra. So this is the better one to use. And the space associated with the circle, space for x is 1, ends up, if you want to put this one, ends up being some hybrid thing, something like the cohomology of x with coefficients in the homology of the base loop space of x. And this is it has a very nice structure of PD algebra and so forth. And probably I want it to be oriented, otherwise Poincaré duality is used. It's with the shift in the grading by Poincaré duality, it's going to be the homology of the free loop space, which minus dx maybe, or plus dx. So here actually, when you do the algebra, it matters first of all which model you chose. And it begins to matter when you look at finiteness and you want to ask what information you keep, what you lose. And you get something fairly obvious, namely the homology of the maps from the circle to x. So it's very easy. You could have predicted it after you see it somehow. All right, so let's see. Let's look at the gauge theory in 3D. In 3D, you can actually, based on this, you can make a guess. Another guess. The sphere goes to the homology of the three maps from S2 into the classifying space BG. Because the analog of the space X was space BG. So BG, the classifying space, is the analog. Bundles over modules over cochains on BG, just like we're looking at modules over cochains over C. And but we write that as the equivariant homology of the base maps, which becomes the base loops in G. And when we write it that way, that's also the correct way to pass to a K the reversion. Because now there'll be a slight difference. This guy. 4D Coulomb branch. It's also 3D actually. That's a guess. And turns out that first of all the guess is correct, but what do I mean by that? After all, it's a partially defined DQFT, and we don't have a universally accepted framework for deciding what's a complete structure we expect for something that's only partially defined. So we have to explain what it means this is the right thing to look at. So it's a correct answer. So let me state the theorem that explains what it's a correct thing. So theorem. Well, first of all, that's the structure of the non-branch. Pre-theorem. It's a theorem, but it's a preliminary structure of the non-branch. Well, actually, let me say that the weak form of the theorem first, so we know where we're going. And then I'll tell you a bit more structure, then I can improve the theorem. So let's preliminary theorem. So if I've used X, so M is a compact symplectic manifold with Hamiltonian G action, then the quantum cohomology of M, I will not define what that is. It's a cohomology of M, some deformed product which counts holomorphic curves, so it's the holomorphic curves. Made equivariant for the G action. It means something obvious because G acts everywhere. Is an algebra over the Teleman homology of omega G. So let me not explain that, but because I need to say more structure. But what does this? Where does this fit in the big picture? Well, at least wishful thinking tells us that to such a thing, you should be able to assign the G category, the Foucault category of Penn. And because G was acting in a Hamiltonian manner, this should be a boundary condition of a three-dimensional gauge theory. So this category itself generates a two-dimensional topological field theory, which is known as Gromov-Witten theory of M. That's a wishful part. That's only strictly true for very special method. Let's believe that. Now G acts on that, so this should be like a representation in a topological sense of G on a category. So it should be a boundary condition for three-dimensional gauge theory, and this tells you, hey, look at the connection here. We've constructed this interesting algebra from three-dimensional gauge theory, and it always acts on everything coming from two dimensions with G action. So that's a promising start. There is a lot more structure.
So in this statement, do you need the action to have an equivariant moment map?
Yeah. So I said Hamiltonian, but I probably.
But yeah, but Hamiltonian.
Right, Hamiltonian.
No, but
Yes, you do. Otherwise it will not be true that G acts in the Foucault category in topological. Hamiltonian. Now, when you can change the moment map, changing the moment map will change the action. So this part of the day. Okay, to tell you more, I have to give you a structure of the Coulomb branch, and this is a much older result by Bezrukavnikov, Finkelberg, and Merkovich. Before the term Coulomb branch was coined or gained currency in mathematics, at least, they had described it without calling it the Coulomb branch. Once it got called the Coulomb branch, it became very popular. So, that was the idea, the value of coming up with cool names. All right, so first, some spec of H star G of omega G, and here we'll have a K-theory version. K star G of omega G. So it maps obviously to spec of the homology of a point, or spec of the invariant K-theory of a point. And this is the complexified D algebra of the Cartan of the Weyl group. So D containing G, the T is a D algebra. And this is, of course, a complexified torus mod. So these maps are obvious. I haven't told you anything that wasn't obvious. But the next thing that's obvious from the structure, so these are group schemes. So let's call these guys the Toda bases. These two guys are the bases. So group schemes over the Toda bases. I still haven't said anything yet. That's not obvious. It's simply because I'm using
the convolution problem.
The convolution here, but there's also a coproduct on the homology, which is comes from the diagonals, that gives a group structure. So far I've said nothing, but now I'm beginning to say something, which is there. The total space are smooth. The maps are flat. And I put a star here because you have to make a little change in K-theory. So you need to, if G is not simply connected, you have to make a change. Just don't worry about that. If G is not simply connected, need a change. You need to turn this into an orbifold, basically. The maps are flat. The total space has symplectic form, degree 2 in this case, degree 0 there. The total space is symplectic forms. Degree 2 in cohomology. And these are the forms which give the E3 structures. Poisson forms of degree -2. Symplectic forms of degree. It's not obvious they'll come from symplectic forms. It's a calculation that they're really symplectic, not just Poisson.
Sorry, they're degree 2 in both cases?
Sorry?
They're degree 2 for both?
Yeah, but degree 2 means degree 0 here, so
Yeah.
there's nothing to say.
Oh, you mean because it's Z2 grade?
Yeah, so. So
what do you mean
sorry?
that it gives the E3 structure?
The symplectic form gives E3. So the symplectic form of degree 2 gives the Poisson form of degree -2, and that gives E3 structure. So I told you earlier, these have natural E3 structure from being mapped out of the sphere.
But I mean, gives a E3 structure means you're using the formality of the E3?
Oh, you mean you're objecting to the fact I haven't put...
No, the question is, are you quantizing, because there are two things you could mean, right? You could say we quantize the two-shifted Poisson structure and we get an E3 algebra, or you could say we use the formality of E3 and...
I'm using formality of E3 here, yes, I haven't quantized anything yet. I want to use quantization.
I mean, they're equivalent, right? But
I just want to use the term quantization for something else. Let's think of formality of E3. So let's see where E3 is the same as Gerson has 2 Gerson.
Two Gerson.
That's what I'm using. But that's correct. I mean, it's if you're over the integers, that would not be, this direction would not be true. The other way. This E3 structure will give a Poisson form, and the Poisson form happens to be symplectic, although integrally I'm not sure if it's really right. Certainly their theorem only check the complex case. Let's be safe here. Actually, proceed on the base. Let's be safe. So the E3 structure is defined integrally, but the geometry I'm describing now stops making sense progressively as I make things more precise. Where are we? The symplectic forms we know as a group structure, okay, and then if you know integrable systems, the obvious next thing is also true. The obvious next thing being the fibers. The fibers will have to be smooth at this point because they're groups over the flat group schemes. The fibers are Lagrangian, as are the identity sections. So there's a section 1. That's also Lagrangian. As is the identity section. And in characteristic 0, there are even abelian group schemes. There are abelian group schemes. Genetic fibers are tori, and they are isomorphic, in fact, not to the maximal torus of the group, but to the dual torus. And they degenerate progressively. The special fiber, the special fibers are the equivariant homology of the loop space with the equivariant K theory of omega G. So in the semi-simple case, just a vector space. The complete degenerations. In some case. Oh, I can say one more thing. Tell you roughly what they look like, but I may not erase this because I want to continue it. So let's say they are birational to this, or birational to a cotangent bundle of the dual torus over the Weil group, or the torus times the dual torus. So there's some kind of affine resolution, affine symplectic resolution of singularities of these guys for the obvious symplectic forms. Are even symplectic vanish. In the torus case, of course, exactly this. There's no biloop. It's a good toy example. And to some extent, what I'm going to say next is going to be an abelianization of the other Coulomb branches. What you're seeing here in this space that generically torus groups to some vector space generation, that's the maximum complexity in a sense, because everything else you learn from other Coulomb branches, we'll do this in a second, you would have seen from the abelian torus and the biloop already.
So the fibers are not just regular centralizers?
The fibers are regular centralizers of the fibers of what? Hang on.
The first guy.
The fibers are a regular centralizer where? In the dual group.
In the dual group.
The dual group, yes. And the fibers here, if you say it correctly, will be regular centralizer in the dual loop group. Okay, from the loop group. You have to be careful how you say it. You cannot say the loop group of a Langlands dual group. You really have to say the Langlands dual of the loop group. There's a difference. That's the one thing I didn't explain correctly in that paper. They did a very complicated thing because they tried the obvious thing of describing them to Langlands dual group and couldn't, so they had to make some amendments first. If you go to the affine description, you can say it in one go, but actually, I vaguely remember you get the wrong algebraic structure from there. I think it's one of these things where you get the correct holomorphic structure by wrong algebraic structure. The difference between connections and monodromies, that sort of thing that comes in. So you have to be a little careful. This guy requires a bit more care with algebra. Alright, so this is what we know about this space and this beautiful structure, and now I'm going to finish the theorem here. This quantum cohomology is an E2 algebra. This guy just is an E3 algebra. And the algebra structures are compatible. In other words, this E3 algebra actually matches the center of the E2 algebra. So there's a notion of an E2 algebra being compatible with E3 algebra. Actually, the intuition is actually pretty easy. And what does the mean you have an E3 algebra? It means you can put algebra objects at points in space, multiply them, and product makes sense. Makes sense meaning when you move them, you get homotopies with the results. For E2 algebra, it will be the same with points in the plane. So E2 algebra being compatible with E3 algebra means you can take a half space, you can put algebra objects in the E3 algebra in the half space, algebra objects in the E2 algebra on the boundary, and the product makes sense. So you can move some things around. You can move this guy to the boundary here, you can rotate around, you can go to the half sphere if you want. So you get a lot of topology from it, but that's it. So let me give, this will be the core of the characterization of the more general Coulomb branch. Let me give maybe a moral explanation of where this comes from. So, to give a moral explanation, it can be made precise, but that is how you make it precise. So if G acts on a magnitude X, then LG of course acts on the Coulomb space of X. So it acts topologically, so LG acts topologically on the homology of the Coulomb space of X. I should say chains. Now what quantum cohomology is a way to make the homology of a loop space finite by using holomorphic disks. So QH star of X, also known as Fleur homology, is the version, a finite version of this. particularly if you're lucky, it should carry a symmetry to the structure you want. So you can expect, and it's actually true, that LG acts on the quantum. So that means, what can we do with that? We can form a bundle over the classifying space of LG with fibers, interesting bundle of fibers. You want to go on. Yes. But what is this guy? G is connected. The same as is G semi-direct product of the base loop space. You get the loop here once. So it's the same as a space G, B of omega G, equivariant with respect to the conjugation action of G on itself. So it's the same as a G equivariant bundle over G. This is G, and G acts like conjugation. Here you have the identity, and you have this bundle of fibers. Now, a flat bundle over a manifold is described by its monodromy representation. In this case, equivariant, so you will get a complete description by taking the fixed point one and describing its monodromy representation equivariantly for the G action. So this datum is actually equivalent to the G action on the fiber H star G. My M became X at some point. So kind of that's how you would at least led to the result. To describe the action, you can just follow the intuition, but of course you have somewhere to use techniques of symplectic geometry, and I don't want to say too much about it, but let's say maybe one precise statement is the fiber of this bundle at the point G in G is the Floer homology of the symplectomorphism induced by the loop action on X. That's a canonical way to describe the bundle, and the techniques from Floer theory allow you to reproduce the entire structure. Okay, so this guy is what we call the Coulomb branch for gauge theory of G for the zero representation. We did not add any additional fields, zero representation. And you see in what sense it describes and is described by two-dimensional gauge theory. Every symplectic manifold with Hamiltonian G action can be sort of placed inside there. And actually you can sweep out the entire Coulomb branch by such manifolds. It turns out, in fact, this space is foliated in Lagrangians by the flat varieties of the group itself. So it's a bit like a complete system of irreducibles built from flat varieties. So in this case, you do have the reverse thing I had mentioned earlier. You can describe this part of the 3D theory from its representations, which is, I think, it counts as success because it's not axiomatically obvious that should be the case. So you can describe a higher dimensional theory in terms of lower dimensional theory. There are examples for it. Okay. So we pause to see, because now I introduce the new stuff. This stuff. Any questions? Now, physicists tell us that there are other versions of gauge theories. They call this pure gauge theory. So physicists assure us things like Coulomb branch of G, or representations E, where E is a continuum representation. And the special case, that's the one that is now well understood, is when E is a double of a complex representation, E plus B2. So there are two questions here. How would we, assuming the negation theory would matter, as they call this, like matter fields, is less well understood, so it's a little less clear what we want to write. And it's also less clear what has to do with anything. So I like to do things, I want to describe the Coulomb branch, and second to tell you its meaning, again in terms of good negation. So I should say the first description was given by Braverman. Penn with the first candidate description. And I probably won't have time for the details anyway, it's explained very nicely in that paper. It's in terms of the equivariant homology, not of the base loop group, of something slightly more complicated. We may call it L sub V, complex coefficient, or we could put A as well, where L sub V is a linear space over omega G, a G equivariant linear space of omega G, G equivariant. I'm saying a linear space, not vector space, because it's stratified. It's a vector bundle over a natural stratification. Vector bundle jumping dimensions. And it's a Borel-Moore homology, so otherwise, of course, fibers are contractible, so you would see anything jumping dimensions over structure.
What's the stratification?
It's the stratification where instead of omega G, interpreted as a moduli space of GC bundles over, that's a sign that should kind of get rid of that. Oh no, it's on my side. Maybe somebody else's.
You was going to give us something.
Then GC over the disk with doubled origin. And now as omega G, right? You should write as Laurent loops over Taylor loops on both sides. And this has, so I mean this space is homotopy equivalent to omega G, like the algebraic, they're exactly the real algebraic loops in fact for natural algebraic structure of G. And the orbits are countably many, the orbits of this group act are countably many, and the linear space has jumping across the strand. It's equivariant, in fact, with this big group.
And the fibers of the vector bundle are?
Yeah, the fiber, I can tell you what the fibers are too, although you won't be able to get the ring structure for this.
So these are bundles on the formal bubble, not on the actual bubble.
So these are bundles on the, it doesn't actually matter whether you take the formal disk here or the affine line, this center. But what matters is the double origin here. Topological is still a sphere.
Yeah, okay.
But you cannot describe this, that is measured as in very soon. But if you write P1, you will not be able to build their space, whereas in my description I'll be able to describe the space from P1. So let me just say the fibers of the bundles. Just that. So the fiber of LV at group gamma in omega, let's say omega algebraic, omega algebraic of G. You do roughly the same thing with the vector space V. So you take Laurent loops and divide twice by Taylor loops, but one of them being twisted by gamma, so you can write a complex of this case Z. And the map is, one map is the inclusion, and the other map is subtract the twist by gamma, or you can write just one map here going to be of Z over There's principal parts, and the map is just gamma minus gamma. Okay? And LT is the curve. So it's infinity. If it's an algebraic loop, it shifts Fourier modes by a finite amount. So the fiber LP always has finite codimension inside, but the codimension will jump as you jump on the strata. And because you take Borel-Moore homology, you have the fundamental class of the fiber. It's infinite dimensional, but let's pretend we don't notice that. But we'll notice that it jumps as you move from an orbit to another. And that jumping, it gets actually smaller. And making it smaller is the same as capping an Euler class of some complementary bundle. So somehow you're extracting a subring of the original ring, which on each stratum is sort of capped by some Euler class. But it's put together in a way that's not so transparent, topologically. But that's the space they proposed, and they proved lots of nice properties for that. It's singular usually. It is Poisson, but it's singular, and it has an action of the original group scheme. But it gets difficult to understand the singularities. But let me tell you now the interpretation and the easy description, which is a bit lucky. So, interpretation. I won't be able to explain it, but so this is, so let's say that, so let's put it this way. So for any compact G manifold, symplectic G manifold M, the quantum cohomology, the covariant quantum cohomology of M across the vector space V. It's a complex representation, particularly it's symplectic in a unique way, is an algebra over the Coulomb branch of G of the representation of G. Incompatible way, so the P3 structure here is compatible with the P2 structure here. Compatible. And the remark, maybe I'll just write an example for it. It is not true if you use the Coulomb branch for the zero representation. It's not true for Coulomb branch of G 0 in place of that. So what is true is that the symplectic cohomology of M cross T is an algebra over this. And the symplectic cohomology in this case is going to be a localization of the equivariant cohomology, more or less inverting the Euler class.
Can you say what this statement looks like if M is a point?
If M is a point, you can just say that the equivariant is exactly the same thing. Let me do that example. For G is U1, and V is the, I won't have time to do a general representation, but that's the standard rep. For example, G is 1, V is C standard representation. Then quantum cohomology G of V is just the ordinary equivariant cohomology of a point, because V gives you nothing, so just polynomials in a variable I call tau sub tau in H2 of V1, the derivative. Symplectic cohomology of V is the Laurent polynomials. And the Coulomb branch of G and the zero representation is just something I erased a long time ago, but it's a Lie algebra times the dual torus, there's no Weil group. So it's just functions of tau, the variable we had before, and z plus minus, that's the coordinate of dual torus. 1. And the way the symplectic cohomology sits inside is this guy is a graph of the function z equals tau, or you is the differential of the function tau times log tau minus 1, and people who know linear symmetry will know where that comes from. The Legendre transform of the superpotential of C, or the differential of tau equals Z also. If you read, so you can read it in two ways. This is the algebra. So you can read it as the graph of a function coming from here, or the graph of a function coming from there, is Lagrangian, so it's got to be a differential of some sort of differential function. So you see the superpotential for the mirror of the representation, or the transform. The Coulomb branch for the representation is going to be two copies of this guy glued together. And the missing point here is going to be at infinity. So somehow, Coulomb branch of V1 and V plus V check in this case is going to be, so this stays here. We're going to have a generically the torus, and over 0, you will have two axes. And your mirror is going to be like that. Z equals this is a mirror. And I have to rush now, but I'm getting to the elementary description of the new Coulomb branch. So let's just state the theorem. The Coulomb branch C of G in the representation of the polarized case, B check, is the obtained by gluing together two copies, the affinization, I should say, affinization, the ring of functions on gluing together two copies of the Coulomb branch of G and 0 by means of a shift. Right? So remember the Toda base. Here was the original Coulomb branch, the group structure and identity, by a Lagrangian shift. By a section, a rational section. Epsilon V determined, I would say formally, from the index bundle of V. So determined formally from V. And the meaning is that the index bundle on V1 of the associated bundle. It has singularities over the zeros of the order class of V. And by taking the original copy and another copy shifted by something which has poles, you're introducing some modifications along the fibers where we have poles, just like here, which in general add points and produce singularities. So that's the description. Last thing I can say, this section is a mirror of V. It's, if you like, the spec of the equivariance effect. So glued together, if you want an algebraic description, it means you only keep the functions on this space which remain irregular after you translate by this rational function, which tells you that they have to have some vanishing conditions at special points so they don't blow up after you translate by a rational function. This is almost equivalent to what seems to be gone, that it acts on the quantum cohomologies of manifold times V. It's almost equivalent to that. All right, I'm already over time, so I'll stop here.
Thank you. Questions? Yeah.
What happened to the DG categories that you introduced?
Well, the category, which is like this, a DG category, but in simple examples like this, I mean, you're just Right, if you take, well, I have to be a bit careful. If you take things like flag varieties or vector space or recurring varieties, you end up finding categories that are generally semi-simple. So somehow the interesting structure evaporates.
Right.
But in principle, I'm saying that this is the graph of the ocean cohomology, and the Fukuyama category is meant to live over that. And there could be derived structure in the fibers, or even possibly in the formal neighborhoods of its support. So that would be there.
More questions? Let's thank Konstantin again. So tomorrow there is another talk, and as Konstantin gracefully pointed out, it was scheduled for 3 a.m., which was a typo, so now it's scheduled for 3 p.m.